All right, hey guys. So today we're going to go through some stuff about inductors. This is like kind of a new but fairly important set of stuff. So first of all, I'm going to go through a review of the stuff for Formula about how a transformer works, just the concepts from it. So you have an iron core with two coils of wire around it, primary and a secondary. The primary coil, so if you have to have a changing current, okay, it's not important, it's not constant, it has to be changing in some way. So it could be AC, or you could just be switching it on or switching it off, or it could be just increasing or decreasing somehow. Okay, but it's a changing current is important. So you have a changing current, that will then cause a changing magnetic field, a changing current in a coil. A current in a coil produces a magnetic field. A changing current produces a changing magnetic field. So you've got a changing magnetic field in the primary. Now, the point of the iron core is that magnetic field is then transmitted throughout the entire core. So you've got a changing magnetic field throughout the entire core. And the important part of that is that means you then get a changing flux in the secondary coil. And if you have a changing flux in a coil, by Faraday's law, you're generating an EMF or voltage in that coil. So a changing current in the primary, you get a changing magnetic field in the core, you get a changing flux in the second coil, so you induce voltage in the second coil. Okay, and you can, by changing the number of turns, you can change how big that induced voltage in the secondary coil is. But what I want to talk about today is something a little bit different. If we take that, what if we removed the second coil? What if we just have this? What if we just have one coil around an iron core? What happens to that chain of logic? So if we go through that same set of steps, if we have a changing current in the primary, well, in this case, it's the only coil, it's still going to produce a changing magnetic field in the primary. The thing that's a little bit different here is that is actually causing a changing flux in the primary. So the changing current causes a changing magnetic field, so a changing flux in itself. So that means if you've got a changing flux in that coil, that's going to produce an EMF in that coil. So just going through those steps. So you've got a changing current in a coil that produces a changing flux in the coil. The change in flux induces an EMF in the coil. Now, the important thing to remember, by Lenz's law, that induced EMF, that EMF that's been produced there, will oppose the change that produced it. Okay, so for example, the change that produced it was initially the changing current. So if that current was increasing, for example, then that EMF would be oriented so that it would slow the rate of increase. It wouldn't stop it, but it would increase at a slower rate, and vice versa. If the current was decreasing, the EMF would be the other way around, so that it would act to maintain the current. Okay, it would still decrease, but not as quickly. Okay, so we get this effect of whenever you change the current in a coil, it produces an EMF that opposes whatever it is you're trying to do. That induced EMF, because it always opposes the change, it's referred to as a back EMF. So you change the current in a coil, you produce a back EMF that opposes whatever it was you were trying to do. Okay? And a coil of wire used in that way is called an inductor. So it operates based on the same kind of logic, same principles as a transformer, except you've only got one coil. Okay, and we call it now an inductor. So let's have a look at how they behave. So inductors, just starting with, what are they? It's a coil of wire. That's it. A coil of wire is an inductor. Usually it's wrapped around an iron core because that increases the strength of the magnetic field and makes it more effective. So we could have ones that look like the one we were just talking about. You could have like that sort of double-sided thing, but without the second coil on it. Okay, that's an inductor, but that's not how they're generally made. large inductors are generally made something like this, with a central iron core that sort of connects around on the sides to strengthen the strength of the magnetic field. And small inductors tend to be made literally just you get a chunk of iron and you just wrap a bit of wire around it. Okay, and that's an inductor. So they could look anything like that or other things. The circuit symbol looks like this. So a series of there's 3 in this diagram. There can be more or less, 3 or 4 or 5 or whatever. It doesn't really matter how many of the little, semicircular hoops there are. So that is indicating a coil of wire, and the line across it is indicating that there is an iron core in it. You could also have the symbol that was just the semicircular hoops connected together. That would indicate it was just a coil of wire with no iron core, but they almost always have an iron core. Now, if we go and look at the theory behind these, we can apply Faraday's law to this situation, because we're talking about a situation where we've got a changing flux in a coil. And the EMF that's induced, in this case, we're talking about the back EMF, is equal to the negative of the rate of change of flux divided by the change in time. The only problem is that if we want to apply that, flux is not something that we can really measure directly, especially not if we're interested in what's going on inside a coil of wire, and that coil of wire is filled up with solid iron. We can't actually get into the middle of the core to measure the flux. So while that is, the definition of Faraday's law and the back EMF that's generated, in a practical sense, it's not actually terribly useful because we can't measure flux easily. But what we can do, we can link the flux to something that we can measure directly. Okay, so what we know about flux? What we know about flux is that it is directly proportional to magnetic field strength. Flux is magnetic field strength times area, and the area is not changing. So if we doubled the magnetic field strength, we'd have double the flux. So they're directly proportional. And something we know about magnetic fields is, we haven't been through this, but take my word for it, magnetic field strength in a coil is proportional to the current. So if we doubled the current in the coil, we would have double the magnetic field strength, and so we would have double the flux. So that means we can write that the flux is proportional to the current. So we can write it like this. We can define flux as some constant times the current. And that constant, we use the symbol L for that. Okay. It's called self-inductance is the name of that constant. More commonly, we just call it inductance. Okay. The unit for inductance, it's actually Webers per amp, which is Tesla meters squared per amp, and it's getting more complicated now. So we just do our usual thing where we smush it all together and name it after a dead guy. In this case, Henry, can't remember what his first name was. He was an American. Anyway, so we measure this constant L in Henry's. Okay, now L is quite complicated. It depends on lots of different things. So basically anything that will change the strength of the magnetic field in a coil changes L. So things like how many turns there are in the coil, how thick the wires are, what the core's made of, whether it's just like what material it is, and also how it's generated, how thick it is, if it's in laminations like we talked about, cores tend to be, what the temperature is. Magnetic field strength is hugely dependent on temperature. So, and lots of other things as well. So it's not something that you can easily write a formula for based on the properties of the coil. It's usually something you measure experimentally. So literally you make a coil and you put some current through it and you measure the magnetic field strength. Okay, so if we use that and we plug that in to Faraday's law, so if we start with our normal sort of minus change in flux over change in time, and we replace the flux expression with L times I. Now, because L is a constant, it's not going to change. So the delta Li on the top, the only thing in there that's going to change is the current. So we can move that L out the front, and we get an expression like this. It's minus L delta I over delta T. So this is actually an expression for Faraday's law. This is Faraday's law expressed for an inductor with an inductance L. Okay, so the terms in here, we've got the induced EMF, I should say actually back EMF in that case, is equal to negative of the inductance multiplied by the change in current divided by the change in time. Okay, and so in this case, we're just representing the change in flux is proportional to the change in current, and L is the constant that relates them. And also remember that negative sign is there. It's negative because the back EMF always opposes the change in current. So if the current is increasing, the EMF is trying to slow that down. Okay. All right. So we can use that to do some calculations. So if we go to look at that law. So if we take our Faraday's law for inductors, and let's say we had this situation. We've got a current through a 4.26 Henry inductor increases from 1.22 amps to 3.48 amps, and that takes 0.200 seconds. Calculate the back EMF induced in the inductor and explain what effect this back EMF will have. So let's start with the calculations. So if we're just going to apply Faraday's law, and we just plug in the numbers, okay? It's minus the inductance is 4.26 Henrys. The current, the final current was 3.48 minus the initial current, 1.22, to find the change in current, because remember it's the change in current we need, and that took 0.200 seconds. So it gives us a change in current of 2.26 amps, and that gives us an EMF, an induced voltage, induced back EMF of 48.1 volts, okay? And that 48.1 volts will be acting against the increase in current, okay? I should say that will be the average induced voltage during that time, because we don't know how that current increased. If it increased at a constant rate, then it would produce a constant back EMF. If it increased in some sort of changing fashion, then there would be like a changing voltage, and that would be the average. Okay, now what effect does that back EMF have? So the induced EMF acts to oppose the increase in current that produced it. Okay, so the increase in current is being slowed, so that reduces the rate that the current increases at. It'll take longer to reach its final value, but it won't stop the increase altogether. Because if you think about that, in that respect, if you induced enough voltage to stop the current altogether, then nothing's changing, and so you wouldn't be inducing anything. It's kind of a logical contradiction. Okay, so it just reduces the rate that the change happens. It makes things take longer to change. All right, so one other little aside here, just real quickly, you also talk about the energy stored in an inductor. So similar to capacitors, the capacitors store energy, so do inductors, okay? Capacitors store energy in the electric field between the charged plates, and in a similar way, inductors store energy in the magnetic field. It's inside the coil. And I'm not going to go through the derivation, but you can calculate the amount of energy stored by the formula 1/2 Li squared. So L is the self-inductance and I is the current. Okay, so for example, if we took that same numbers from before, we had our 4.26 Henry inductor and the current got up to 3.48 amps. How much energy is stored in the magnetic field? So the energy is 1/2 Li squared, and if we plug in the numbers, we've got a self-inductance of 4.26 Henrys and a current of 3.48 amps, gives us 25.8 joules. That's how much energy would be stored in the magnetic field. Okay, so that's sort of the basic stuff. One thing that's interesting to know about inductors, this is kind of almost just safety information, but is also could be applicable in an exam situation. You need to be very careful when you switch off an inductor, a circuit that has an inductor in it. Sort of almost ironically or unexpectedly, inductors are far more dangerous when they're switched off than when they're switched on. Now, that doesn't mean it's the act of switching those. When they are turning off, that's when they're dangerous. The reason for that is when you open a switch, the current drops from whatever value it is to zero very quickly. So it's not no time. It does take a finite amount of time for the current to change, but it's a very short amount of time. So if you think about if you have a circuit with an inductor in it, and we apply Faraday's law, if you've got a very, very small change in time, and L and the change in current is still going from the same current down to zero, your delta I is the same and L is constant. If you've got a small change in time, that means you're going to get a very, very large induced EMF, okay? In fact, that induced EMF can greatly exceed the voltage of the power supply, okay? So like even with a circuit with that's powered by like a 9-volt battery, you can induce hundreds of volts when you switch it off if there's an inductor in there. Okay, so there's a risk of electric shock when you switch off an inductor, but that effect can also be quite useful. It's quite important, in fact. Spark plugs use this concept. So the large back EMF induced when you open a switch is used to generate the high voltage needed for spark plugs. Okay, I should say the large back EMF induced when you have an inductor. Like it doesn't happen when you turn off a light switch because there's no inductor in the circuit, but if you have an inductor in the circuit. Now, spark plugs need like tens of thousands of volts to actually generate a spark, but a car battery is only like 12 volts. There's not enough voltage from the car battery to actually make a spark, so you couldn't ignite the fuel. Like I said, tens of thousands of volts are needed to do that. So they use a circuit with inductor. Actually, they use a circuit with a transformer, which has similar properties. So this is like a simplified version of the car ignition circuit. So there's like two halves of the circuit connected around by the transformer. You've got in blue there what's called the low tension circuit, which is like in car phrasing, they call it low tension. Physicists would just call it low voltage, powered by the 12-volt battery. So it's got essentially a 12-volt battery, a switch, which is kind of complicated how they do that, but it's basically just a switch, and it's connected to the primary coil of a transformer, and it's a step-up transformer as well. The other side of the circuit in red here is what's called the high tension circuit. It's the high voltage circuit, which is essentially it's just the secondary coil of the transformer connected to the spark gap, which is at the bottom of the spark plug inside the cylinder of the engine. So the process that actually happens here is firstly you close the switch. Okay, that makes a small current flow in the primary coil. Okay, not much. It's only a very, very small. Okay. Now, nothing really happens at that stage. Okay, because when you close the switch, you've got it connected to a coil of wire, the primary. The primary induces a back EMF, okay? And that makes the current take quite a while to build up, okay? Because it's taking a while for the current to build up, the rate of change of flux in the transformer core is quite small, so the secondary doesn't really do anything, okay? It won't generate a huge amount of voltage at that point, and even if it does generate voltage, it won't be enough to cause a spark, okay? But you've now got current flowing through the primary coil. Okay? Now, the important thing happens, the next bit is when you open the switch again. Okay? So there was current flowing in the primary coil, you've just opened the switch. So the current in the primary coil rapidly decreases. The important term there is rapidly. It happens quickly. It's not necessarily a large change in current, but it is a rapid change in current. So you get a rapid decrease in flux in the transformer core. So the flux drops from whatever value it was to zero quickly. Okay. That means you get a rapid collapse of the flux in the secondary coil. And that, combined with the fact that the secondary coil has a lot more turns than the primary coil, you get a very large voltage in the secondary coil. Okay. Tens of thousands of volts, enough to get a spark across the spark gap, and that ignites the fuel, and that makes your car go. Okay. So that's just a little bit about one of the sort of uses of this idea of that sort of applicability of Faraday's law to inductors. So again, this is like a transformer, but it uses those same ideas of the rate of change of flux and the rate of change of current. Okay, so stuff here for you to have a go at. There's some stuff on Education Perfect, properties of inductors. It shouldn't take too long. And you've been set that on Education Perfect, and there's a link in the Google Classroom for you to that.